The purpose of my observations is to gather data to allow for the assessment of the shape of the Earth's surface. This presentation is organized in a scientific experiment format, as seen in the table of contents below. Starts with a hypothesis, the math, experimental methodology, the atmospheric considerations, the observational information of the experiment, the results and data, a bit of discussion, and then a conclusion. Hypothesis. If globe, the surface must curve at a specific rate, based on the radius of the Earth of 3959 miles. The math. If the surface curves, objects in the distance must get hidden beyond the globe's physical horizon. A simple metric is how much should be hidden, simply called hidden height, which is an easily calculated value given observer height and distance. The experimental methodology. First, find a good location and conduct repeated observations from that location. Repeated observations provide evidence for the assessment of factors such as atmospheric refraction, which is highly variable. It's known to sometimes raise and sometimes lower distant objects. Atmospheric considerations. The physics of downward refraction. If one observes a superior mirage in the background, it can be inferred that there is a temperature inversion with cooler air under warmer air between the observer and the mirage. This also produces a looming or towering effect, as well as fata morgana. The light's just hitting your eyes at a higher than actual angle. Again, when there's a temperature inversion, some of the light from a distant object refracts downward and hits your eyes at a higher than actual angle, as shown in this diagram below. Occasionally, one can observe the temperature inversion line created by the interface of higher density cooler air and the warmer air above. It becomes pretty obvious, as shown in the picture below. Here's a few examples of downward refraction from my repeated pans. This optical effect is almost always limited to the background elevations. Another example here. Here's another example of downward refraction. This one's kind of interesting. We've got Hogan at 17.8 miles, and there's a slight superior mirage right above the rig here. And there's also, looks like there's a band of looming over here. There's a line here and a line here, maybe a temperature, you could call it a temperature inversion, I guess. But it looks like it's being stretched upward in this zone. And another example of downward refraction. In this case, we've got a tree that's being loomed upward and then a superior mirage above it. That's at 30.6 miles. The tree's at about 280 foot elevation. You know, in some cases, I'm speculating there's a layer of warm air, then cooler, then warm air here, because you get some, what looks like, stooping or sinking along the base of the rig here and even along the ridge. And here's another good example of downward refraction. In this case, it's a superior mirage or fata morgana above Clark's Peak. That's about 55 miles. The peak in front's about 50 miles. That's La Jolla Peak. And then Platform C right there at 13.1 miles. But these effects are typically limited to the background only. And the last example of downward refraction, this one's pretty good. It's fata morgana above Laguna Peak down there, about 49 miles from UCSB. It's right above Magoo Naval Air Station. Those are the domes and the top of the peak there reflected upwards. So the light from those objects are actually hitting your eyes at a higher than actual angle. The physics of upward refraction. If one observes an inferior mirage, like a hot road in the summertime, it can be inferred that there is warmer air under cooler air in that area between the object and your eyes, along your line of sight. It's also referred to as upward refraction. This produces a sinking effect and apparent downward displacement of objects in the distance, the light from the distant object hitting your eyes at a lower than actual angle. Can I really infer there's warm air under cooler air along the line of sight between my camera and the inferior mirage? So I asked Google AI the same question. See the answer down in the yellow highlighted area below. It says, observing an inferior mirage at a distance of 25 miles, that's just an example, confirms the presence of this specific atmospheric condition, warmer air under cooler air, along your line of sight. This is just what you see is what you get. Here's another diagram depicting upward refraction. In this case, it discusses a vanishing line effect where some of the objects in the background get obscured by the mirage. This diagram was created by Life is Short channel on YouTube a few years ago. It explains why things are hidden bottom up in the distance. For example, refraction over water is almost always refracted upward. It creates a sinking effect. So, like it says at the bottom, you will most often see buildings, boats, landscape, oil rigs appearing lower than they actually are. Some of the light gets lost into the surface, so you're not going to see the bottom of the object. In general, the normal condition of the atmosphere supports sinking and inferior mirage, or upward refraction, as seen in this diagram. You got warmer air on the surface to cooler air in the atmosphere. The surface warms up, especially around towns. You got roads with asphalt, that type of thing. The opposite is called a temperature inversion. It's called an inversion because it's the opposite of normal. So you've got cooler air, then warmer air, then cold air above. Here's a description of what a temperature inversion actually is I found online. It supports that the normal condition is temperature decreases with height. So you got warmer under cooler air as normal. And again, it's called an inversion because it inverts the normal condition. You can read the rest of the text. Here's a few examples of upward refraction from my pens. In this case, inferior mirage. It's really obvious when you see an inferior mirage. You get the rounding effect on landscape that intersects the waterline. And another example, same place. This one I believe is taken in the morning time. But also you can see that the rig here, the boom on the right, is reflected below. And you get the rounding effect again over here. Here's another example of upward refraction. In this case, we've got two locations at the same time, a few seconds apart actually. In this case, we got La Conchita Beach and the spot with a slight inferior mirage below it. And then down here at Ventura at the tree, a very slight inferior mirage, but it's causing sinking, and you can't see the legs of Hogan here because of that downward displacement. And another example of upward refraction. In this case, it's just a little bit more inferior mirage than the previous one. Again, these two images are taken a few seconds apart. Here's La Conchita Beach and the spot refracted below with an inferior mirage. And then down at the tree, a more obvious inferior mirage effect with the rounding again, hiding just about the same level. The vanishing line's right about the same level as the tree. It's about 280 feet. And you can see the boom over here on Hogan is refracted in the foreground below it. Over a year ago, I found a site online that provided modeled sounding data, which is temperature versus altitude data for an area near Magoo Naval Air Station. And I was trying to correlate that data to what I saw in my pans. In this case, it's the same day and same time. They updated the data hourly, but a really strong inferior mirage this day, which indicates warm under cool air. And you can see it here at 56 feet. You got 14 degrees, 14.3, and then it cools off quickly up to 1,000 feet, about 3 degrees, I guess, across 1,000 feet. The data is no longer available. The site went dark, and it's kind of a bummer, but it is what it is. Observational information, camera location. So I shoot from University of California, Santa Barbara, or UCSB, parking lot number 6. So this is the parking lot. More recently, my camera is set up right about where the red dot is. Previously, it was set up right over here, about 100 foot to the north. GPS coordinates are right here if you want to check it out. This image depicts the field of view from UCSB, looking mostly east, southeast. So I start past the Mesa Lane Beach area and the cliff, looking down at La Conchita Beach here at 22.7 miles, and then I pan over this direction to Magoo Peak. So the tree would be right here above Ventura. The ridge is over in this area here at 50 miles, with the oil rigs in the middle here, the lower 3 and then the upper 4. This is the Peak Finder rendering of my view from UCSB. So over here we've got the Mesa Lane Cliff with La Conchita Beach in the background, over to the tree above Ventura, and across the pesky ridge here, all the way over to Magoo Peak. You can note that this ridge is actually shown as it is. The first time I started looking at Peak Finder years ago, this ridge was actually hidden, as was Magoo Peak for the most part. They've changed the rendering to raise it up to make it look more actual. This slide shows evidence of the elevation at UCSB where I shoot from. This is off a map of UCSB. It shows a 41-foot elevation at the parking lot. And this is from my camera showing a 40-foot elevation. So you add 5 feet or so for my tripod. I'm at about 45, 46 feet. But, the tide varies quite a bit. We've had king tides lately at 7 feet and then downwards of minus 2 feet when they get low. The sample size of my repeated measures is currently at 138 pans. Most of those pans are across different days. But there's quite a few where I've done 2 a day, especially recently. Do note that I only video when I can see the far shores. Much of the time across summertime, for example, it's really too hazy. So really the season goes from, let's say, October to April, May, into June sometimes, but then it gets just too hazy and foggy to see anything. My camera equipment, I started out with a P900, like most folks, and then switched to the P1000 a couple of years ago. I really like the P1000. You just got to be careful with the focus and lock it once you get zoomed in. The picture on the right shows my camera at UCSB at my typical location. Results and data. So I picked 3 targets in my field of view. This one is the spot above La Conchita Beach. It's a landscape feature. You can see it here on the right above La Conchita Beach. This is a community. These are the stables over here. It's taken from Rincon Point surf spot by this guy here. He's an excellent photographer. Anyway, the spot's estimated to be about 100 feet above mean sea level. It's 22.7 miles from UCSB. It's about 98 degrees as the view angle from UCSB. The globe hidden height is 140 feet, so nominally without any refraction, it should be below the horizon. The view's 99% across water. Globe horizon would be at 8.2 miles. Here's a view of the spot I took from driving south on Highway 101. The highway's about 20 feet above La Conchita Beach, and here's the spot, around 100 feet to 125 feet above mean sea level. These are the stables, and to the left is the community of La Conchita Beach. The distance to the spot from UCSB is 22.7 miles. Target number 1, data. This is for the spot. I summarized all of my pans and created a histogram, as can be seen on the left here. It's categorized as visible above the apparent horizon, hidden by inferior mirage, or too hazy. So as you can see here, 97% of the time the spot is observed above the apparent horizon, even though it's in the zone of the hidden height for the globe. So 3% of the time it's hidden by inferior mirage or haze only, never by what appears to be an actual physical horizon. This histogram summarizes the appearance of an inferior mirage at or below the spot. So you can see that 30% of the time an inferior mirage is observed at or below the spot. Here's some examples of inferior mirages below the spot from my pans. In this case, you can see that the ears, I would call it, from the spot, these two little upward protruding areas here are reflected below. Pretty obvious. And another example here with the spot being reflected down below, this one right above the apparent horizon here. And even these little areas here are in the reflection, and this area is rounded right here. It's pretty obvious you've got an inferior mirage right there. Here's another example of upward refraction with an inferior mirage below the spot. In this case, I'm highlighting the displacement of the background, the sinking effect, stooping, whatever you want to call it. But basically, not only is the spot brought down, but part of the background moves down as well. Occasionally you can see Highway 101 traffic below the spot. You can see the trucks moving along here in cars. So in this case there's a truck right there. On clear days and when there's less upward refraction, you can see the horizon moves upward here a little bit. Yeah, and that allows the highway to be seen clearer. Here's another example of the highway below the spot. Here's the spot, and here's a truck on Highway 101. That's about 20 feet above mean sea level. Spot again is about 100 feet. Target number 2 is called the tree. It's on a ridge about 30.6 miles from UCSB. The elevation's 280 feet. The globe hidden height's about 334 feet, which would be above the grove here that's to the left of the tree. The view's about 99% across water again. The view angle is 105 degrees from UCSB, and again the globe horizon would be at 8.2 miles. The Highway 33 goes back here to Ojai from Ventura. This is called Taylor Ranch. Here's another shot of the tree taken from Ventura by Brent Flatten. Yeah, I love the name, right? So I just like it because there's surf in the picture, but the tree's on this ridge above Highway 101 down here, and this is Taylor Ranch. That's the grove here. Yeah, beautiful picture. And here's another shot showing the location of the tree on the ridge above 101. Taylor Ranch here. We've got Surfer's Point, or it's called C Street by a lot of people. There's a nice swell running. That's why I like the picture. That's pretty big, actually. Looking up the coast, you've got Pitus Point here, Rincon. La Conchita's tucked back behind this ridge here, and I'm shooting from way up here. The distance to the tree is 30.6 miles. Here's UCSB. Here's the tree on the ridge. And then Platform Hogan's at 17.8 miles. Platform Hogan's, I guess, the most northerly rig out of the lower three. The elevation of the tree is about 280 feet above mean sea level. This is a topo map. You've got Highway 101 at about 80 feet, I think. And then you got the tree sitting in the middle of this part of the ridge here. It's right in the midpoint, so that's about 280 feet. And then the grove sits right along here at maybe 320 feet. Globe hidden height would be up here about 334, I believe. Here's Taylor Ranch. The tree is observed above the apparent horizon approximately 84% of the time. The other 16% of the time it's hidden by an obvious inferior mirage, or it's just too hazy to see. About 1/3 of the time, an inferior mirage is observed at and below the tree, sometimes hiding it, as mentioned in the previous slide. You can see here the trees just on the vanishing line of the inferior mirage, and the mirage is seen below the tree. It's also below this boom here on Platform Hogan. Here's another shot of the same effect at the tree. You've got the tree above the apparent horizon, an obvious inferior mirage. This is a boat here, Platform Hogan. Sometimes the whole elevation from the water line to the tree is observed. You can see part of Highway 101 right here. It's harder to see at 30.6 miles, but we see it occasionally. Target number 3, the Pesky Ridge. The elevation of the ridge is somewhere between 900 and 1,000 feet, right about here. It's just over 50 miles. The globe hidden height at that distance is 1,160 feet, so it should be below the horizon when we've got a uniform density atmosphere in this area. The view is 70% across water, and then the last 30% is across the low-lying land of Ventura, Oxnard, and Camarillo, generally under 70 foot above mean sea level until it hits the elevations in the background. The view angle is 108 degrees, and again, the globe horizon would be at 8.2 miles. The distance to the Pesky Ridge is 50 miles, as shown here in this slide. The ridge is right about here. UCSB is here. You can also see how the last 30% of the view is across this low-lying land here, basically from here over to the ridge here. This shot's taken from a hill above Ventura. This kind of gives you a perspective of that view across land and then the ridge. This is Conejo Peak here. Saddle Peak, which is in the background when we're viewing the Pesky Ridge, is way down here above Malibu. That's 72 miles. This is a elevation profile between UCSB here and Saddle Peak. It shows the elevation from UCSB until it hits the land at just over 30 miles here in Ventura. As it crosses Oxnard, Camarillo area, it stays generally under 70 feet until it hits the foothills. And then the Pesky Ridge here is at about 900 to 1,000 feet at just over 50 miles. And then Saddle Peak back here, just above Malibu, is 2,789 feet at about 72 miles. Target 3, the Pesky Ridge, results in data. The ridge is observed well above the apparent horizon 100% of the time across all types of observed refraction effects. Downward refraction, upward refraction, combination of the two. 29% of the time, an inferior mirage is observed below the Pesky Ridge. You can see one here at Henry, for example. As I note here, I use Platform Henry as a reference because it's really difficult to assess inferior mirage or upward refraction effects below the ridge, but it's always there, as mentioned in the previous slide. Here's another example of an inferior mirage indicating upward refraction in the line of sight between my camera and the Pesky Ridge. You can see here the boom on Henry is starting to reflect down here above the waterline. And another example here of upward refraction or an inferior mirage in the line of sight between my camera and the Pesky Ridge. Here's Henry again with a very severe inferior mirage. You can see the rounding here. So that's being reflected down here. And another one. In this case, I contrasted the view toward the tree and Hogan here with the same pan with Henry and the pesky ridge. So you can see a real severe inferior mirage here and even at Hogan, and then over here again at Henry. Occasionally, the whole elevation of the pesky ridge is observed, distant shores to the ridgetop, as seen below. Here's the distant shore, let's say 35 miles, somewhere in there. It goes, stays under 70 feet until it hits the foothills, and then ramps up pretty quick to 900 to 1,000 feet here. But you can see the whole elevation here. Bonus observation, the three-point lineup. Just to the left of target 1 is the cliff face at Mesa Lane Beach. It's 6.5 miles from the camera. A feature on this cliff has been estimated to be about 45 feet above mean sea level. It's pretty easy to figure that out. Other folks have looked at it, and we all agree that right below the nose on that cliff is where 45 foot should be. Occasionally, it lines up collinear from my camera to that cliff face and the houses at La Conchita Beach. So that's 3 points of equal elevation. Again, the camera, the cliff face, and the houses at La Conchita Beach, all in a straight line. 3 points define the line. It's not the only place that this happens. It also happens between the oil rigs and the distant shores. Here's a few examples of a three-point lineup. So my camera's at 45 feet, cliff face right here about 45 feet, and the houses at La Conchita Beach with the spot above here. The spot's at about 100 feet. The house is, so 20 feet or so of house above, 20 foot of highway down here. And another example. Another example here. We've got the cliff face at about 45 feet here, 6.5 miles, and the houses at La Conchita Beach along here and above the highway at 22.7 approximately, with the spot well above the beach and the highway down here. When we have a three-point lineup, as in this example here, my opinion is that it kind of fits my mind's eye. The foreground ramping up to the distant shore in near perfect perspective. It just looks right to me. Here's a three-point lineup example with the oil rigs and the distant shores. In this case, we have platform C on the left, and the distant shore is about 36 miles. The 45-foot elevation on the rigs is approximately right here at the top of the legs, and you can see the buildings down at the distant shore lines up directly with that. And here's another example of a three-point lineup with the oil rigs and the distant shores. In this case, it's platform A, and then right there at the Mandalay Power Generating Station, 36 miles away. So again, we got 14 miles and 36 miles lining up at the same elevation as my camera. And now for the discussion part. So globe specification geometry, based on a globe with a 3959 mile radius, where the target is physically hidden by the alleged horizon, is never observed at the spot, the tree, or the pesky ridge across both observed upward and downward refraction effects. So there's the tree with inferior mirage, upward refraction. There's the tree on the ridge with downward refraction effects in the background. Conversely, the three-point lineup, which is a flat Earth expectation, is occasionally observed, typically without any obvious upward or downward refraction effects present. The globe explanation for observing the spot, the tree, and the pesky ridge above the alleged globe horizon is looming or towering caused by downward refraction, raising it in the background above the horizon. And as confirmed by the data presented in 6.1, 6.2, and 6.3, that would be required 100% of the time. So here's a couple diagrams. Downward refraction is depicted raising a ship over the horizon, and in this case, a mountain over the horizon, so you see it above the horizon instead of below. It is also sometimes claimed that we observe these elevations and targets above the horizon due to standard refraction based on a standard atmosphere. Note, this standard refraction is just a baseline reference as mentioned in the text below, and the temperature profile actually supports upward refraction, not downward. So here they're talking about standard refraction based on a standard atmosphere. You can see they're showing a downward refraction effect, not an upward, which is typical with warm under cool air. However, as previously described, the observed presence of an inferior mirage confirms upward refraction conditions are in effect. So far, it's been 1/3 of the time across all my pans, and that directly correlates to the only instances of the spot and the tree being hidden. Here's an example of seeing elevations in the distance that should be below the horizon, well above the horizon. And this is the famous Canigou from Marseille, France. So you can see here that in the image, he's explaining that the light's following a downward refraction path to your eyes, so it effectively raises the Canigou up into the line of sight. However, the images here show the effects of a inferior mirage. All four of these shots here, taken at different times, show a severe inferior mirage at the base of Canigou. So this is the Mediterranean Sea here, right? And that's warm air. I mean, the Med's pretty warm, and that's a 9,000-foot mountain. So you got cooler peaks. So you got warm under cooler air, which is upward refraction. If anything, these peaks are brought lower, not higher. Most importantly, if the target is lower than or at an equal elevation as the globe's nominal hidden height, you'd never see it when confirmed upward refraction conditions exist. None of the light from the object, here's an object at the hidden height, none of the light would make it over the horizon. It would get lost into the surface on the far side of the horizon from where you're observing, in this case at UCSB. The target would be displaced lower, not higher. This is a true globe refraction paradox. In other words, most globe supporters claim downward refraction is in effect all the time, but we can confirm we've got upward refraction effects occurring in a zone of elevation at or below an object in the distance that should be below the horizon. A while back, I was having a discussion with someone on YouTube in the comments about this globe refraction paradox. He was having trouble understanding it, so I explained it a couple times. And he eventually asked the same question to, I think it was Gemini AI, and this is the response. So what it's saying is the same thing I'm claiming, is that it's not possible to see something that should be below the horizon that has a inferior mirage effect in front of it with upward refraction. Take a look at this paragraph right here. Lastly, globe defenders often measure and compare vertical angles of targets in the distance, and they usually use a total station, or in this case a bubble level theodolite. They either point out the height ratios are wrong or the dip angle, that is an apparent horizon or distant feature that appears lower than level, correlates or proves the globe. But due to the nature of both upward refraction and downward refraction effects causing looming, towering, sinking, stooping, compression, and the like, in my opinion, measuring angles is folly. Finally, a conclusion. My observations never support globe specification geometry, ever. Taken all together, they logically support a flat surface. It's really that simple. I'd like to give a shout out and thanks to these YouTube folks. My apologies if I've left you out, but I'm just listing some off the top of my head here that I've had a lot of interfacing with. So we've got Bo at BMLSB69. He's the OG Black Swan guy, if you remember. And then Ben at Taboo Conspiracy, who's featured some of my work. Thanks, Ben, for all the support. Got Dave at Wide Awake. Hang tough, Dave. Your work in Florida was groundbreaking and beautiful as well. And then Travis at Plain Truth. He's a refraction guru, the ether band guy. Love you, Travis. You got B Flat. He loves to discuss refraction as well. He does great work and interfaces with a bunch of folks online. And then the couple at Sky Free doing short range observations and demonstrations, really showing how much downward displacement can occur with warm under cooler air. Life is Short channel from a few years ago, groundbreaking work on refraction. Paul at Plain Reality from Australia doing great work with horizon perspective type things, how the horizon moves around different times of the day, so forth. He's been on a lot of podcasts lately, doing great work. I love talking with Paul. And then the guys up in Alaska, Speaking the Truth and All There. They do the snowmobile work on the dry lakes. I think they're all coming to the same conclusion we are here. All right, thank you, you guys. Have a good one. Over and out.